The precision with which we can measure GPS positions depends on the GPS positioning method used as well as the satellite geometry. Suppose we use the best dual-frequency receiver and work under the most favorable satellite constellation. Are we guaranteed 100% accurate position results? Not at all. This chart lists a number of sources of error that contribute significantly to inaccuracies in the recorded GPS position. Added together, these errors can cause a deviation of plus minus 5 to 50 meters from the actual GPS receiver position. In addition, when deemed necessary, the Department of Defense may intentionally alter the time and ephemeris signal to introduce up to 70 meters of positional error. Positional errors caused by this so-called selective availability can be removed by differential correction. Some of the other errors may also be partially or completely removed by differential correction. We will talk about differential correction after we have looked at the various sources of GPS position error. Since the GPS signals traveling from the satellites to the GPS receivers must pass through the ionosphere and the troposphere, they are greatly affected by atmospheric conditions. The more time the GPS signals have to spend in the ionosphere and the troposphere, the greater the delay in their travel toward the Earth. Therefore, the distance derived from signal speed times time will be different from what you would expect if the GPS signal just passed through empty space. This effect is more pronounced for satellites that are at lower elevation angles. Another source of error is the distortion of the signal by measurement noise. This can introduce from 0 to 10 meters of positional error. I mentioned earlier that GPS signals contain information about ephemeris, or orbital position, errors, and about the rate of clock drift for the broadcasting satellite. The data for the satellite may not exactly model its true satellite motion or the exact rate of clock drift. The disparity in ephemeris data can introduce 1 to 5 meters of positional error, and clock drift disparity can introduce 0 to 1.5 meters of positional error. Some of the ionospheric effect, and most of all the tropospheric effect, can be removed by differential correction. Ephemeris and clock drift errors can also be removed by differential correction. GPS receivers require a line of sight to the satellites in order to obtain signals necessary for calculating the distances to the satellites. Therefore, any object in the path of the signals has the potential to interfere with the reception of those signals. Think about tree canopy, buildings, and terrain features. In addition, reflective surfaces can cause the GPS signals to bounce around before arriving at a receiver. This also introduces an error in the distance calculation. This type of error is known as multipath error and can be caused by a variety of materials, notably water, glass, and metal. Even the water inside the leaves of vegetation can produce multipath error. In some instances, operating under heavy, wet forest canopy can degrade the ability of a GPS receiver to track satellites. Multipath errors cannot be removed by differential correction. Adding a ground plane or a choke ring that blocks or redirects stray signals from the GPS antenna may be helpful in some situations. The GPS user should be aware of potential multipath errors and try, as much as possible, to collect data under open sky and away from objects that can reflect the signals. There are several data collection techniques that can minimize the effects of signal blockage by tree canopy or other objects. For example, many GPS receivers can be instructed to track only the highest satellites in the sky, as opposed to those that provide the lowest DOP. Increasing the elevation of the GPS antenna can also dramatically increase the ability of the receiver to track satellites. Unfortunately, there will be locations where GPS signals simply are not available because of obstruction. In these cases, there are additional techniques that can help to solve the problem. Some GPS receivers have the ability to collect an offset point, which involves recording a GPS position at a location where GPS signals are available, while also recording the distance, bearing, and slope from the GPS antenna to the position of interest where the GPS signals are not available. This technique is useful for avoiding a dense timber stand or building. Another method employs a traditional traverse program to record manually entered bearings and ranges and generate positions until satellite signals can again be received. This position data will be tied to the position data collected with the GPS receiver. A plus-minus 50 meters of uncertainty is not acceptable in many applications. How can we obtain higher accuracies? A technique called differential correction is necessary to get accuracies within 1 to 5 meters, or, even better, with advanced equipment. Differential correction requires a second GPS receiver, a base station, collecting data at a stationary position on a precisely known point, which typically is a surveyed benchmark. Because the location of the base station is known, a correction factor can be computed by comparing the known location with the GPS location determined by using the satellites. The differential correction process takes this correction factor and applies it to the GPS data collected by a GPS receiver. Differential correction eliminates most of the errors listed in the GPS error budget we discussed earlier and allows GPS positions to be computed at a much higher level of accuracy. There are two ways of applying the correction factor to the GPS data you collect. The post-processed method applies the correction factor after you have finished collecting and storing the raw GPS data. The corrected positions are computed during post-processing. The real-time method applies the correction factor as you are collecting data and lets you store corrected positions in the field. GPS helps us quickly locate positions by measuring distances to satellites that orbit the Earth. However, just the positions themselves may not be of great interest to us. If I just tell you 44 degrees latitude and 123 degrees longitude, you will probably want to know what is at that location. It does not make much sense if I just tell you where something is without telling you what that something is. So, let me inform you that Pleasant Hill is located at 44 degrees latitude and 123 degrees longitude, just outside the city of Eugene. Your CMT GPS data collector will let you record not only the location, but also a name for that location. It will also let you record additional descriptions for that location. When you record both the location and the description of a geographic feature, you are collecting GPS GIS data. A Geographic Information System, GIS, provides information for describing and mapping geographic features. It is basically a descriptive database of the Earth, or a specific part of the Earth. GPS tells you that you are at a point XYZ, while GIS tells you that at XYZ there is an oak tree, or a spot in a stream with a pH level of 5.4. GPS tells us the where. GIS tells us the what. With the complete knowledge of where and what, we are empowered to locate, organize, analyze, and map our resources. In transportation applications, GPS assists pilots and drivers in pinpointing their locations and avoiding collisions. Farmers can use GPS to guide equipment and control accurate distribution of fertilizers and other chemicals. Recreationally, GPS is used for providing accurate locations and as a navigation tool for hikers, hunters, and boaters.